Okay, let's solve the wave equation. Solve the wave equation. Let's look at the acoustic wave. This will be solved using the backward time central space finite difference scheme, but we have to give some. Let's solve this for x element of 0 to L and t greater than 0. Let's assume that p of 0 comma t equals 0. So we're going to have a, so we assume that p of 0 comma t is 0 here, and p of L comma t equals 0. So no value of the pressure here, no value of the pressure here, but we can see what happens in between. That's the Dirichlet boundary condition. Now let's have an initial condition P. So let's write it here. So P of x0 equals, let's assume it's some Gaussian kind of a thing, exponential, or I can say exp open bracket minus x minus L over 2 squared, for example, over 2 sigma squared. Sigma is the spread of the pressure, is the width of the spread. Now, how do we go about this? Well, first you can let solution now solution. So let some value q. So step 1, let's call it step 1. Step 1, deduce, let's call this equation 1 maybe. Deduce equation 1 into 2 coupled equations. How do you do that? Let some value q. Let's write it here. Let some value q equals the derivative of pressure with respect to time. So that means dq by dt is this, right? Because now this is q. So this means, so let's call this 2. So this means dq by dt is what you have as the right hand side of equation 1, c squared d squared p by dx squared. I hope you understand, or otherwise we get equation 1 back in here so you can see. That's the trick. You first have to convert them into coupled equations. So this is the major equation, paste. This is the major equation, but then you assign q to be this, and then if q is this, then to get the right hand side you differentiate q by t to get this. Then we now apply the backward scheme. So how does the backward scheme go for this one? We have q of n j minus q of n minus 1 by dt. If you remember, that's the backward scheme. So that's the backward scheme. But the issue here is you are going to, yeah, that's the backward scheme for this guy. So that is going to be c squared dp. Yeah, so this time we have to apply, because we did not apply anything here. So but p will still have n anyways by dx squared. So that's what you got. But also the central scheme for second derivative of p is p of j plus 1 n minus 2 p of j plus p of j minus 1, here all in n, over dx squared. Already multiplying c squared. So we're going to put all of this in here, and what we have is we have q j of n minus q j of n minus 1 over dt equals c squared into p of j plus 1 n minus 2 p of j n plus p of j minus 1 n. We can, like we said, you have n and n minus 1. That means you are looking at n at n minus 1. Using n minus 1 to get n. So instead, we can let n equals n plus 1, so that now this one, when this one become n plus 1, this one will become n plus 1, but n plus 1 minus 1 will be this. This one will be n plus 1, n plus 1, n plus 1. Why is this done? This is done in order to be able to solve using the methods that are available. So this is necessary. You're dealing with a backward time scheme, and like we said, it's quite difficult to manage, and therefore we get this. All right, so you have now, you can push this guy to go to move forward. You can have this situation. So q n plus 1 equals c squared dt, right? Oh no, here there is dx squared from there, dt by dx squared p j plus 1 n plus 1 minus 2 p j n plus 1 plus p j minus 1 n plus 1 plus q j n. All right, or you can even let it be there, but we're going to see what happens next. Right now, but we know that from here, no, not this one, from here, you know that, so we can say, let's copy this guy down. We have this guy, we can say but q equals dp del t. When we use the forward difference for this guy, we can say that when we use the backward difference, we can say that Q J N equals P N J minus P N minus 1 J over delta T. And like we did for the top one, we can say let N equals N plus 1 here, and then this guy will be N plus 1, then this would be N plus 1, and this would be N, and that's it. And from this equation, what is the name of this equation? Let's call it equation 3, and we can call this 4. We can now substitute this guy here, and then we end up with this equals this. Yeah, so we end up with this. Right, now that we have this, we would like to set Pn plus 1 here, and we move all, we want the order of n to be in one side and the order of n plus 1 to be in another side. So what do we have here? So this guy goes there and this guy goes there, so we have Pj n plus 1 minus, so let alpha equals c squared delta t by delta x squared, so that this would be alpha. All of these guys will be alpha, minus, and then the dt will go up as well, so we have to say dt squared maybe, and so minus p of j plus 1 n plus 1 alpha, this guy would go here, and then plus 2 alpha pj n plus 1 for this guy coming to the other side, then minus alpha pj minus 1 n plus 1 equals, this guy goes to the other side, pnj plus qjn delta t. We can rearrange this, so we have minus alpha pj plus 1 n plus 1 for this guy, and then plus 1 plus 2 alpha for this and this, pj n plus 1 and minus alpha pj plus 1 n plus 1 equals pjn plus delta t qjn. That's the recursive relation. This is an implicit scheme. We have to be able to organize it in a way that we solve for a, we in the form ax. First we have to make it look ax equals b, and then we find a, which is x inverse times b. This is easy. You just do numpy dot linear algebra, and then you get it. But before we apply before we arrive there, we have to first look at the initial conditions. The initial conditions, we know dp of x 0 by dt equals 0. I think I wrote it somewhere here. Oh, I didn't write it. Okay, anyways, let's use this initial condition. And because because here Q is dp dt, so you are, because Q is del P by del T, when you say del P by del T, so you're just trying to say that Qj of 0 will be 0. And let's look at another initial condition. P of x comma 0. Let's set this to be some f of x. So this means Pj of 0 will be f of x in this our scheme, in this our iterative scheme. And so we have this and we have this. Now let's look at the boundary conditions. The boundary condition P0 of n equals 0, because here is 0, here is 0, so this is P0 and this is Pn, right? But you cannot say Pn because you are going to have a situation like this. We have to look at the boundary conditions properly. But first let's do it. P0 of n equals 0, P0 of n plus 1 equals 0, Pn of n equals Pn of n plus 1 equals 0. Alright, it's just trying to tell you that if you have, this is P0 of n plus 1, for example. Let's say we are in iteration Pj0. So we are going to use the n plus 1s as this suggests. So because if this is 0, then this would be 0 plus 1. So P1, for example. Now you have this. This will be P1 n plus 1, P2 of n plus 1, P3 of n plus 1, P n minus 1 of n plus 1, and then Pn of n plus 1. So this one is 0 and this one is 0. That's what we mean here. And also if you are in the 0th condition, so Pn of 0, whatever the case, whatever you are doing here is 0. That's just the boundary condition. The ends will have no pressure. And if you are using because we are using a 3-point formula, this is a 3-point formula, this one, it's using, if you look here, it's using j plus 1, j, oh yeah, one of them must be j minus 1. I think this one is j minus 1. It's really good that we are here, back here. So this is j minus 1, and then this is j plus 1, and then this is j. So at any point in time you are going to have 3. So when you are at this point, you are going to have the j. What is the coefficient of the j? This guy. This is the coefficient of plus 1, this is the coefficient of minus 1. Let's use the coefficients. So if I'm here, I only have here, I cannot have this guy because I can, but I have initial condition. So why don't I start here? So when I start here, so I'll be here 1 plus 2 alpha minus alpha. This would be 0 because I already know that one. Then I'm moving to the next. I'll be here. So 1 plus 2. So here will be 0, 0, 0, like this. 1 plus 2 alpha minus alpha. Here would be minus alpha. Here would be 0. And then I'm going here. And I'll have 1 plus 2 alpha minus alpha minus alpha until the end. In the end, I will have 1 plus 2 alpha, but this is 0. The zeros will come here, and I have minus alpha. These are also zeros. So I end up with a matrix that is, so I can have a matrix like this. And that's the idea. So what do we get from our, let's copy this guy so we can see it clearly. Copy. Paste. So what we see is this. We see PJ. I want to flip it. I want to start writing this one. So we see, let's say PJ 0 plus delta T QJ 0. So at each n, you are going to have this matrix. So at each n. So for n equals to 0, for example, for n equals to 0, you have this PJ 0 plus this PJ 0 plus delta T QJ 0 until you reach. So what do you see here? We have ignored this guy, and we have ignored this guy. So you are, and also we are going to have a situation like this. We're going to have a situation like P n minus 1 0 plus delta T Q J 0 nice. Okay, equals, now here you're going to have those matrices 1 plus 2 alpha minus alpha 0 dot 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 minus alpha, just like this matrix, minus alpha 0 dot 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 0, and then 1 plus 2 alpha dot 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 0. Then you reach the end, then you have minus alpha 1 plus 2 alpha. That's a tridiagonal matrix. And what do you get here? You get multiplied by, so here is PJ plus, so you have a situation like this, like you have P 0 1, then P 1 1, then P 2 1, and dot dot dot, then P n minus 1 1. That's what you get. These ones are known for n is equals to 0. These ones are known from the boundary conditions and initial conditions. These are known from constants. These are unknown. And what you would like to do is call this B A X, and then you want to solve the equation X equals A inverse B, and that's it. Now in the what do you call it, in the boundary conditions, this Qj0 is 0. So when you go to the boundary conditions, you will have in the beginning Qj0, so you set this to 0. And what do we have more? Where is it? Can't find it. Oh yeah, this one. Yeah, that's what led to this, right? P0 of j equals f of x. So here in the matrix, Pj0. So this one will be f of x. That is for n equals to 0. For n equals to 1, already you have the P0. Then you can always use that P. You can always use this relationship to estimate Qj, because you will always have what you need. And in the beginning you use the boundary conditions. What next? And that's it. And in the end, when you reach the end, you have a metric like this. You also apply the boundary conditions.